consider an inductor which is carrying a current IL through it, inductor of value L, and there is a voltage across the coil EC. And we have discussed while discussing converters how to find the value of L using the Faraday's law. The Faraday's law related to electric currents, EC is equal to L dIL by dt. So the rate of change of current into the inductance will give you the voltage across the coil. Now, is it possible to get the value of inductance L from the other parameters, physical parameters and magnetic parameters of the inductor? Now, that is what we will try to find. See, typically this is a circuit symbol, what we have written here. In reality, you will see that there is a core, as I said, a ferrite core or a CRGO core or any of the magnetic core materials, on which you will wind some turns, and it will have these two terminals just like here, and then a current will go in through and come out. This is IL, and voltage across the terminal will be the voltage across the coil EC. And this coil may have N turns, and within the core it will set up a flux d phi by dt. And this core will have some pre-designed value of permeance lambda shown here. Now, with respect to such a physical fabricated inductor, what is the value of the L, or how is L related to these core parameters and physical parameters? So let us go back to the fundamental equation. Phi is equal to permeance into MMF. Recall, for as a comparison, you can jog your memory using charge Q is equal to CV. Phi flux is equivalent to charge Q, permeance is equivalent to C, MMF is equivalent to the potential, and that is what this equation is. Now, phi is equal to permeance into MMF can be written as NIL. Let me now differentiate this equation. d phi by dt equals permeance constant, N constant, dIL by dt. Now, let me multiply both sides with N. So, N d phi by dt is equal to permeance, now N square, dIL by dt. Now, if you look at this, this is nothing but Faraday's law, EC, which is equal to N d phi by dt, voltage across the coil. And what is this? Would also be equal to EC, and we see here the Faraday's law from the electrical perspective, which is L dIL by dt. So this is of the form L di by dt, and therefore this L must be equal to this, permeance into N square. So the inductance is equal to permeance into N square. See that inductance is related to the permeance magnetic properties and the physical properties. And this is an important relationship. We'll be using it in design of the inductor. Remember this. Now let us expand permeance. L is equal to permeance is mu naught into mu r into AC, core cross section area, into N square here, and divided by Lm, the mean magnetic path length. So you see that the inductance is related to the permeability, the core cross section area, the number of turns, mean magnetic path length, all the physical and the magnetic properties. So this is one way of getting the L from the physical magnetic properties and the physical properties. The other way is to get from L dIL by dt, which we obtained from the electrical requirements of the converter. So these two we have to map and match to fabricate the inductor. Of course, let us see how we will go about do it, some more fundamentals, and then we can design the inductor. Let us now discuss the energy that an inductor can handle. From the electrical perspective, we know that EL, let's say EL is the energy in the inductor, is half Li square. I is the current at a given instant. So this is the instantaneous energy at an instant when the current is taking some value I. So half Li square is the energy in the inductor, and this is coming from the electrical perspective by virtue of the motion of the electrons. Now let us see if we can get the energy in the inductor from the magnetic perspective. Now half Li square can be written as half Li can be written as Ni by N whole square, which is equal to half L. Ni is nothing but MMF, so MMF square by N square. Now what is L by N square? L by N square is nothing but permeance, because we know that L is equal to permeance into N square. So this is nothing but permeance. So we can write half permeance into MMF square. So this is the magnetic perspective for the energy in the inductor, half permeance MMF square. This is half Li square from the electrical angle. Consider the electrical equivalent potential storage. How does it look like? We know permeance is equivalent to capacitance, so half C, and potential MMF is nothing but voltage. So this will translate into an equivalent as half CV square. So we can be satisfied that the equivalence works. Now let me further introduce the small modification, permeance into MMF. I will take that together into MMF. Now permeance into MMF is nothing but phi flux, half phi into MMF. This again from the equivalence you can say it is half QV. So here again equivalence works. So you see that half phi MMF is still the energy. Now phi I want to express it in terms of flux density B. So let us say half into AC into phi by AC. Phi by AC is the flux density B to MMF. So I can write that one as half into AC into flux density B, this one, and into MMF. So this becomes the energy that is stored in the inductor from the magnetic perspective. Now let us say AC for a given core, AC is fixed, and for a given core, let's say ferrite, BM, the maximum operating flux density BM can be fixed. As I told, for ferrite we can fix it at around 0.25 Tesla. So like that, if I know the core type, core material, you can fix this BM. So these two are fixed constants. So then energy is directly proportional to MMF or current, because MMF is N into I, N is again a fixed quantity. Energy is directly proportional to the current. So greater the current, greater will be the energy that can be stored in the inductor. So how do I increase the storage capacity of the inductor? So let us see that one. It is of interest for us to see that for a given size of the core and flux density, we would like the inductor to handle more and more energy. So let us understand this by drawing the BH axis, and let us take a typical core where you have the BH curve like this. This is the saturation, negative saturation, and this has a slope of permeability mu or mu1 in this case. So let me fix the operating flux density. So this is the operating flux density on the positive side. We will call that one as BM. Likewise, the operating maximum flux density on the negative side minus BM. So we know that the flux density in the core will swing only between minus BM to plus BM within that and never crossing that. So if we limit the flux density to this value, what is the maximum energy that this inductor can store? So if you take the intercept here the field will be NIL I1 by LM. This is the H field at this point. So when a current I1 is flowing, then we know that the energy stored in the inductor EL1 is proportional to IL1. So this particular core having this mu1 as the permeability can store this particular amount of current for a current I1 flowing through that. Now, can I increase the energy handling capability of this core, which means that I should be capable of handling higher currents, higher MMFs, which means it should go further on into the x-axis. But if you start going further on into the x-axis, the core will reach saturation, it will start flatten out, and there is no induction, and therefore permeability is 0. So how do you still keep the flux in operation without saturating the core and still be able to store larger energy? So let us see what happens when you reduce the permeability mu. So let us do that. Let me draw another line here, so which is having a lower slope, and this intercept here. You see, for the same BM, the intercept here for this lower permeability core where mu1 is greater than mu2, this is N I2 by Lm. And here also, let's say the energy EL2 is proportional to IL2. So we see here that the energy at this point for this particular current being handled for this curve, for this core, the green line is EL2 is greater than the energy that can be maximum energy that can be handled by this core indicated by the blue line. So if I reduce the permeability for the same flux BM, this will go and meet the saturation much later in the field axis as shown here. So which means that it is capable of handling higher currents, larger currents, and therefore larger energy. So how do you achieve that? You have to decrease permeability. How do you decrease permeability? By decreasing the permeance. And what is permeance? Permeance we saw is mu naught mu r AC by Lm, the magnetic path length. Look at this mu r. Mu r is the relative permeability, which is the order of 2000 to 2500 in the case of ferrites. Let us say you make it equal to 1. What is it? Mu naught permeance becomes mu naught AC by Lm, which is for free space. So mu r is equal to 1 for air. So if you start introducing air gaps, then my relative permeability value will start coming down for the same core, and the effective permeability mu naught into mu r will start reducing and the slope decreases. And as the slope decreases, the intercept at the BM maximum operating flux density will move further on towards the further on away into the x-axis, and the core will be able to handle higher currents, and therefore the inductor is capable of storing higher energy. So this way we try to maximize the energy storing capability of the inductor. See, one primary important feature of the inductor that it should be capable of storing energy. So that is why we try to design an inductor which is capable of carrying higher and higher currents. In the discussions till now, we have made some equivalence between electrical and magnetic parameters. Let me summarize them so that we understand the electrical and magnetic properties equally well. So the parameters, potential in electrical is voltage, V, or EMF, electromotive force. In the magnetic domain, it is the magnetomotive force. The kinetic parameter or the flow parameter in the electrical domain is current, I, amps, and the magnetic domain it is d phi by dt. Power in the electrical domain is EMF, voltage into current, or the potential into the kinetic variable. Here also it is the same thing, potential variable mmf into d phi by dt, and both have units of power which is watts. This is watts and this is also watts. Capacitance in the electrical domain is C, and the magnetic domain it is permeance. Elastance in the electrical domain it is 1 by C, and the magnetic domain it is called reluctance R, which is 1 by permeance. Charge in the electrical domain Q, which is integral of I dt. Here it is phi. Flux in energy you have half C V square. Half C V square is replaced by half permeance mmf square, or you can club CV and call it as half QV, and here also half phi into mmf. So these are some of the equivalents that we saw. You can write many more equivalents. You will see that because the energy is the same across the domains, there is a very nice strong equivalence between the electrical and the magnetic parameters. Use this equivalence to remember the equations on the magnetic domain.